So in this section, we will be looking at equivalent representations of polynomial and rational functions. Different representations can be useful for different things that we need to find. For example, your expanded form. This would be like if I've got f of x equals 3x to the third minus 6x squared plus 12x. It's all multiplied out. It's not factored. This is often helpful for determining the end behavior. And the horizontal asymptotes. Of a function. This is often helpful. Obviously, this does not have a horizontal asymptote, but in rational functions it may. The factored form, so for example, something in factored form might look more like this. 2x times x minus 4 times x plus 2 squared. Factored form is often helpful for finding zeros. That should have been blank right there. And discontinuities. Those discontinuities are either holes in the graph or our vertical asymptotes. So, whenever we are doing these problems, we are going to need to be able to both expand and factor. So let's start by expanding, and this should be, for the most part, review. So whenever we expand, we're just wanting to multiply everything out. So for this, we would do x times 3x. That would give us 3x squared. Then we would have to distribute this x to the negative 5. We would get negative 5x. Then the negative 2 has to be distributed. So negative 2 times 3x will give us negative 6x. And negative 2 times negative 5 is positive 10. At this point, you want to combine any like terms that you can. So this negative 5x and the negative 6x can be combined. And we'll get 3x squared minus 11x plus 10. This is just a different way of writing the original function. If you were to graph this original function and graph 3x squared minus 11x plus 10, those two graphs will be exactly the same. They're different representations of the same function. Okay. So if we look at number 2, this is an example of something I told you we'd work a little bit more on, of squaring binomials, because this is something I would like for you to be able to do in your head, not having to write it out. If you do write it out, this is what happens. This is x minus 5 times x minus 5. So you would do x times x, you would get x squared. X times negative 5, you would get negative 5x. This negative 5 needs to be distributed, so negative 5x. And then negative 5 times negative 5 is positive 25. And so we would have x squared minus 10x plus 25. So that would be equivalent to the original function. Whenever you do this, you can do this in your head by squaring the first term, multiplying these two together and doubling it, and then squaring the last term. So when I do these, I do them in my head. So to do this, I would just square this first number. X squared would give me x squared. Then I would multiply x and negative 5 together. That would be negative 5x. And I would double it. To double is just to multiply by 2. So that would be negative 10x. And then I would square the last number, which would be a positive 25 for that. So if I use that shortcut here, if I square this first term, 3x squared would be 9x squared. We're going to square the 3 and square the x. Then I would multiply these two together. That would give me 6x, and I would double it, so I would get 12x. And then I would square the last, which would give me a positive 4. So by using that shortcut, you can square, double, square, and you can do this much faster than having to write it out. If you need to write it out, that's fine. I would rather you be correct and a little bit slower than to be fast but wrong there. Now, if I look at example 4, this is a little bit more difficult problem because this is to the third power. So that means what we're looking at is we've got x minus 4 times x minus 4 times x minus 4. So to do this, I'm going to have to multiply all 3 of those together. The square, double, square rule only applies to squaring something, so I cannot like cube, double cube, or cube, triple cube. That's not going to work. But I could put these two right here together, maybe, and square, double, square them. So I would have x minus 4 right here. And then if I square, double square here, because this is just x minus 4 squared, I would get x squared for the first part. Negative 4 times x is negative 4x. I would double that, and I'll get negative 8x. Then I would square the last term, which would be positive 16. Now, I'm not done because I've still got to distribute here. I've got to multiply the x minus 4 times the x squared minus 8x plus 16. So this x must be distributed here. I'm going to get x to the third minus 8x squared plus 16x. And then I have to distribute the negative 4x squared, or negative 4 to the x squared, I should say. Negative 4 times negative 8x will give me positive 32x. And then negative 4 times 16 is going to be, let's see, that'll be negative 64. Okay, and so I do need to combine like terms, so this negative 8x squared could be combined with that negative 4x squared, so we'll have x to the third minus 12x squared. Then I've got a positive 16x and a positive 32x. That is going to give me a positive 48x. And then I've got that minus 64 there on the end. So these would be equivalent to each other. Now, as you can see, that starts to take up a little bit of room. So if I wanted to raise something to the 4th or 5th or 6th power, that's really going to take a long time to do, and it's going to have a lot of room for error because you've got to do so many calculations that it's really easy to make a mistake. So I'm going to teach you guys a shortcut for expanding binomials here that will work on any of these, not just the square, double square problems. So what we have here is called Pascal's triangle. Blaise Pascal was a mathematician long ago, and he came up with this triangle. In the first row, you just have a 1. This actually is called row 0 right here. The second row here, which is actually going to be our row 1, we just have a 1 and a 1. All the edges you see are 1s here. After you get the first 2 rows started, then to make each new row, you're going to put 1s on the end, and then you would add these 2 numbers together. 1 plus 1 will give us 2. You'll notice that continues. 1 plus 2 gives you 3. 2 plus 1 gives you 3. Right here, 1 plus 3 gives you 4. 3 plus 3 gives you 6. 3 plus 1 gives you 4. So that gives you the next row. Then if I want the next row, I've got 1 plus 4 gives me 5. 4 plus 6 gives me 10. 6 plus 4 gives me 10. And 4 plus 1 gives me 5. And this continues on forever. This is infinite. You are probably not going to have to go any further than what you see here. In fact, I'm probably not going to make you use like that last line right there. So in general, we do not find ourselves using rows 0, 1, or 2 very often because those are very easy to raise things to those power. But 3 and beyond are very helpful because, let me show you what we can do here. If I want to raise x minus 5 to the 5th power, to raise something to the 5th power, I would have to write this out 5 times. I'd have to multiply it all together. It would be very difficult to do. But if I want to use Pascal's triangle, what I can do is I can create the triangle. I know we just had it on the last slide, but I'm going to draw it again just make sure everybody knows how to get it. 1 plus 1 is 2 here. Then we'll put a 1. 1 plus 2 is 3. Goes here. 2 plus 1 is 3. That goes here. And then I'll put a 1 on the outside. So this is row 0. This is row 1. This is row 2. This is row 3. We need the 5th row. So we're going to put a 1 here. 1 plus 3 is going to give me 4. 3 plus 3 is 6. 3 plus 1 is 4. Put a 1 on the outside. That's the 4th row. I need the 5th row here. So I'm going to do one more row. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. Put that 1 on the outside. So I'm going to use the 5th, it's really the 6th row, but we call this row 5 here because we're starting on the 0 row right here. And I'm going to use these as my coefficients. So I'm going to have 1, I'm going to leave lots of space, 5, 10, 10, 5, 1. And here's what's going to happen. My x's right here are going to go in descending order. I will have x to the 5th here. I'll have x to the 4th. I'll have x to the 3rd. I'll have x squared. I'll have x to the 1st power. I don't need to write the 1 right there. And then this last term right here is not going to have an x at all. If I wanted, I could put x to the 0, but that's unnecessary. Then I'm going to take this number right here, and it is going to go in ascending order. So I'm going to start with 0 of them and go up. And in between, I guess I should, in between everything, it's going to be a plus sign here for right now. Anyway, so I will not have any negative 5s at all with this first term. If you wanted to, you could put negative 5 to the 0 power, but that's just going to go away. Then I'll have negative 5 to the 1st power, negative 5 squared, negative 5 to the 3rd, negative 5 to the 4th, and negative 5 to the 5th. And now you just need to simplify. So negative 5 to the 0 is just 1. This is going to be x to the 5th. Negative 5 times 5 is going to give me, actually I should have, that's going to give me a negative 25 x to the 4th. Here I have to do negative 5 squared. You got to do your exponents first, so that would be 25. 25 times 10 is going to give me 250 x to the 3rd. Here I've got to do negative 5 to the 3rd. That is negative 5 times negative 5 times negative 5. It's going to give us 125, negative 125. And we're multiplying that by 10. So we'll get negative 1250 x squared. Then I've got to do negative 5 to the 4th power. So negative 5 to the 3rd was negative 125. If I multiply that by negative 5, I'm going to get 625, I think. 5 times 5 is 25. Carry your 2. 5 times 2 is 10. 12 here. Yeah, that'll be 625. It's going to be positive. So we'll get plus 625x. And the last is to the 5th, so I'm going to multiply this by 5 again. 5 times 5 is 25. Carry your 2. That'll be 12. Carry your 1. 5 times 30 is 31. 3,125. That'll be negative 3,125. You should see that if this sign right here is negative, that your signs end up alternating. Positive, negative, positive, negative, positive, negative. That's happening because whenever you raise a number to an even power, it has a positive with it. All right, so this would be your answer right here. It's not incredibly simple, but it is a lot easier than multiplying that all out 5 times. All right, let's try that one more time. Here, I've got 2x and negative 1 to the 3rd power. So for the 3rd row, I'm using 1, 3, 3, 1. This one's going to be a little bit easier just because we're not raising it to quite as high of an exponent. So I have 1, 3, 3, 1. Those are my coefficients that I pull from Pascal's triangle. Put plus signs right here. My 2x right here is going to go in descending order. So I have 2x to the 3rd, 2x squared, 2x to the first power, and then 2x to the 0, you got no 2x's at all there. And then I'm taking this negative 1 right here. I won't have any with the first term. If you want, you can put negative 1 to the 0, but you don't have to. Negative 1 to the first power, negative 1 to the second power, and negative 1 to the third power. So whenever I do this here, when you do 2x to the third, you have to raise 2 to the third power and x to the third power. So 2 times 2 times 2 is going to give me 8, and I'll have x to the third. Negative 1 to 0 is just 0. It's just 1, so it goes away. Here, you need to do your exponents first. You may even need to do this in a couple steps. Right here, you're doing you're going to have 3 times 4x squared times negative 1. And then here, negative 1 squared is positive 1, so this is just going to be 6x for this part. And then negative 1 to the third is negative 1, so you'll end up with a minus 1 here. If we just finish out this little piece right here, we're going to get 8x. Sorry, it's not letting me write right there. Let's write down too low on the page. Let's go over here. We will get 8x to the third. We're going to get minus 12x squared plus 6x minus 1. And that would be equivalent to what we started with here. Okay, so you guys are going to try a few of these on your own, and then we'll continue on with the next.